let's say they're independent. So I showed you last time that if two random variables are independent and I have their product under an expectation like that, then this is equal to the product of the two expectations. So if they're independent, then I can break up this expectation into these two expectations. And because I've given you the mean of the random process over there, what do I have here? What's this value? So expected value x of 1, that's the mean of the process at time 1, which is what? 1. No, it's 0. So I said this is a new process, has nothing to do with the random process that I've shown you in the examples. In this case, the mean of the process at all time is 0. So here it's 0, and here it's also 0. So this is 0. Okay, so we're off to a promising start. If these two random processes are independent, excuse me, if these two values of the random process are independent and we start with 0 mean, then this measure returns the value of 0. So that's kind of nice. Furthermore, the most correlated that those two values could possibly be is if they're actually equal to each other. So now let's say x1 equals x4 always. If that's true, then I have expected value x1 times x4, which is equal to the expected value of, these are equal always, so I can write this as the expected value of x of 1 squared. And this is actually equal to, so remember, the variance of the random process is equal to the expected value of x of 1, x of t squared, minus the mean of the random process squared. But that's 0 in this case. So in fact, this is equal to the variance time 1. So if they're equal, always, if those two, at those time instances, they're always equal, and you can make a similar argument that this is equal to this. So if they're independent, then it's equal to 0. If they're always equal, then it's equal to the variance, which is greater than 0. So that's very interesting. We've discovered a measure that's 0 if they're independent and positive if they're dependent. And you can also show that if they're perfectly anti-correlated, in other words, x of 1 is equal to minus x of 4, by a similar argument you can show that's equal to sigma squared negative the variance minus sigma squared. Furthermore, and I will prove this next time, I can show that so this is, if you like, the most correlation possible. That gives us a value of sigma squared. And this is the most sort of negative correlation possible. That gives us a value of minus sigma squared. And in fact, I can show that this measure of correlation is always between those two variances. I will show that next time. But in other words, I've just discovered a correlation measure. So this correlation measure is 0 if they're independent, It's sigma, and it varies between minus sigma squared if they're maximally anti-dependent, and sigma squared if they're maximally dependent. So this is a pretty good correlation measure. So in other words, this measure tells us whether values of the random process are highly correlated or highly uncorrelated. Okay, so the autocorrelation which we call Rx, T1 and T2, is basically equal to the expected value of X of T1 times X of T2. And basically, as a function of T1 and T2, this will tell you how correlated individual time instants of the random process are. If the mean of the random process is 0, then this will be, and this is 0 everywhere except where T1 equals T2, then you know that the random process is independent. Or each instance of the random process is independent. Any questions on what we've covered up until now? Okay, I'm running out of time, so we will go back over this on Thursday. I will remind you, please help me out with my Twitter experiment. Please sign up for Twitter, and if you do, there's a 1%